Hey everyone, this is Chen Shu from Expressive. Welcome to the talk. I'm the Senior Engineering Manager responsible for the research and development of Expressive solutions for Thread, Zigbee, and Matter. In this talk, we are going to dive into the details of the Thread network protocol and exploring how it works in the Matter ecosystem and learning about the Thread solutions that Expressive offers. So first, we will introduce the thread. What is a thread? In short, thread is a low-power, secure, and IPv6 based mesh networking technology for IoT products. It's built on top of the existing 15.4 PHY and MAC layer, introducing 6LoWPAN and IP routing features, providing a standard IPv6 interface to the upper layers. So currently, Thread supports a single OQPSK file operating at 2.4 GHz and 250 kbps data rate. The Thread 1.1 is based on the 15.4 2006 version, and since Thread 1.2 and later, it requires some new features defined in the 15.4 2015 version, such as the coordinated sampled listening feature, which supports some lower power consumption device types. So I will talk some more details later. Now let's talk about the 6LoWPAN layer. Thread, based on 15.4, provides an IPv6 interface to the upper layer. However, the IPv6 frame is large with 1280 bytes MTU and a 40 bytes IPv6 header and a 4 bytes UDP header. Yeah, so you see the overhead is very big. So to deal with this overhead, the 6LoWPAN adapter layer is introduced to fragment and reassemble IPv6 packets to and from 15.4 frames. The next layer is IP routing in Thread. So before we look into the routing protocol in Thread, let's first take a look at the Thread networking topology. In a Thread network, there are several different types of devices. In this diagram, the devices with blue color are all 4-thread devices that implement the 4-thread function. They could be router devices or REED device. So here, the REED device means it's the device which can work as a router, but they don't act as such at the moment. The devices in black color are minimal thread devices, which only implement the minimal threaded functions to be an AND device. So here, the minimal thread devices cannot be router. They can only be the AND device. These AND devices could be the power device or some sleepy AND devices. So Thread is a true mesh network, meaning any router devices that can hear each other and they can maintain a routing link. So here is the leader. Leader is a special router device. So first leader is a router, but it's a special router device. And each Thread network has only one leader. The leader is responsible for managing other routers, aggregating and distributing network data within its Thread network. The border router is another important role in a Thread network. It provides connectivity to other IP networks. In a Thread network, there could be multiple border routers, and any device with a non-Thread network interface, like the Wi-Fi or Ethernet, can work as a border router. And each Thread network has a set of network parameters. It's known as a dataset. For a device to join the network, it needs to know the network key or the entire dataset. The thread protocol defines a commissioning process to securely commission a new thread device to the network. But in some real use cases, the dataset can also be given to the device via some out-of-band method, such as the application layer commissioning process. So once a thread device has got the network key or the entire dataset, it can start joining the network. This process involves the mesh link establishment flow. In short, we call it MLE. So the MLE protocol defines how the links are established in the thread network and how network data is distributed. So there are several kinds of network data in a thread network. It includes the leader data, like the leader address, partition ID, partition weight, and some other network data includes the on-mesh prefix and some addressing and routing configurations. The MLE is actually carried over UDP. This is a generic format of an MLE message. So in this message, there is a security header and a command ID with the TLV-based payloads. When a new device joins the network, it starts with the attach process, which is also known as the child-to-parent link. This is done through the MLE messages and involves 4 steps, from the parent request, parent response, to child ID request and child ID response. The parent request is a multicast message the device will send and to find the router or REED who can act as its parent. Then the subsequent child ID request and response are used to complete the attach process to get a child ID and to establish the link. Then the device finally joins the network as a child. So it's the first link type. We call it the child-to-parent link. The second link type is the route-to-route link. The routers can establish links with other routers as long as they can hear each other within a single hop. This is done through 3 MLE messages. They are the link request, link accept, or we can put the link request and accept in a same one message. With these links, the 3 devices in a same network could form the mesh topology. And the 4 thread devices, the FTD can switch roles between child and router based on the network's requirement. So any devices will join the network as a child, but the FTD will join as REED. They can be upgraded to the router to extend the connectivity or support new devices join the network. For example, when a new device wants to join, but there is no router which can help, so the REED will upgrade itself to router and support this device to attach to the network. Similarly, a router may downgrade to a child based on certain conditions. For example, when there are enough routers, but not so many children, or when the other routers are enough to replace its router role. So a router device may downgrade itself to a REED. But of course, it can still upgrade to a router whenever necessary. In Thread network, all messages are protected by AES-CCM encryption and authentication with 32-bit MIC. The MLE messages are all protected using the MLE image security, and other messages will use the 15.4 layer frame security. So here is the exception for the commissioning messages. So here comes to the addressing part. Each thread device has several IPv6 addresses using different scopes. The scope includes the link local, which is with a single hop communication. And the RAM local scope is within the thread network. We can also call it the mesh local. And the global scope is used to communicate with the devices out of its thread network. The mesh local addresses are used for routing in thread network. There are two kinds of mesh local addresses. The EID, the endpoint identifier, is a unique identifier which will not change even the network topology changes. But the routing locator, the alloc address, will change based on the topology because the alloc is generated by the router ID and child ID. So let's see an example. So we have two routers with the router ID 1 and 2, and each router has two children. The router ID 1 and children ID 1 generates an alloc address 401. And together with the mesh local prefix, it could generate an alloc address used in the thread network. So here, the mesh local prefix is one of the parameters in a thread network data. After we introducing the network topology, MLE, and addressing scope, now let's back to the routing part. The routing protocol in thread network is the shortest path and any-to-any routing. The routing path is among routers, and the parents will help their children to receive and forward the messages. And here in a thread network, there are no more than 32 routers, which means that for biggest thread network, the biggest router number is 32. And each router in a thread network has a link table and a route table. The link table includes all the neighbor routers and the incoming and outgoing quality of the link. So in thread, the link quality is based on the signal stress. Since there are up to 32 routers in a thread network, the entries in the link table are up to 31. Let's check this example. There are 5 routers, A, B, C, D, E, and B, C, E are A's neighbor, so they are in A's link table. And A also has a route table, which includes the next hop and cost to all other routers. So in A's route table, the next hop for B, C, E are all themselves because they are only one hop. But the next hop for D is E. So any messages from A to D, A will send to E first, and E will help to forward the message to D. But why don't A choose C as the next hop for D? Because the both are two hops. This is because that the A knows the link quality to C is not as good as to E. You can go back to the link table. You can see that in the A's link table, the C's link quality is not as good as A and B's link quality. So in this case, A will consider the cost to C is higher than to E. So A will prefer to choose E as the next hop to D. And all the thread routers will advertise their route information periodically. For each destination, the router will determine the path cost through each neighbor and select the neighbor with the minimal path cost. Route table is dynamically updated according to the network topology and the link quality. So this is the thread routing protocol. Then let's go to the thread, another benefit of thread, which is no power. The thread no power is achieved by some sleep and device types. For example, a sleepy end device, which can sleep for most of the time and wake up to query messages via data request, is defined in the 15.4. The wake up period depends on the application requirements. from seconds to hours. Since thread 1.2, it introduced a new sleepy end device, called the synchronized sleepy end device, which does not need to send any packets after waking up. Instead, it just turns on the IF and receives. So to receive a message, consume less power than to send a message. Of course, the child and the parent should be synchronized on the listening window. This is done by the coordinated sampled listening feature defined in the 15.4 2015 version. So this is how a thread device to achieve the low power consumption. Then we come to the thread border router part. It's a very important role in the thread network. It connects the thread devices to other IP networks. To achieve the bidirectional connectivity, the border router will generate the OMR prefix. It's the off-match prefix, and advertise it in the thread network data. Each thread device will add a global unicast IPv6 address from the OMR prefix. In the meantime, the border router will advertise the OMR prefix by sending a router advertisements to the Wi-Fi network, in which it includes the route information option. So the other Wi-Fi devices know which is the destination to send messages to a device with the OMR prefix. And similarly, border router send a prefix information option, the PIO, in the router advertisements to Wi-Fi networks. And the Wi-Fi devices will add a unicast address based on the Wi-Fi prefix. And also the border router will include this Wi-Fi prefix in the thread network data as an external route. So the thread devices will know if any devices want to be sent to the Wi-Fi devices, they can send the message to the border router since it supports the external route. Then the service registration and discovery is another important feature of thread border router. It makes it possible for devices in thread and other non-thread networks to discover each other using the DNS-based discovery. The border router implements the service registration server, advertising proxy, and the discovery proxy. All the thread devices register their services to the border router, and the border router will help to answer all the MDS queries from the other networks. If a thread device wants to query a service, it can also send a unicast DNS query to the border router, and the border router will help to perform a multicast query from other networks. Generally speaking, all the DNS query and responses in thread network are unicast, which means that the thread devices don't have to stay awake to receive multicast queries and answer by themselves. This helps to save a lot of power consumption compared to the other Wi-Fi or Ethernet devices. Multicast is also supported by a thread network, but it uses an optimized protocol called MPL, which is designed for the low power and lossy networks. The thread devices register their multicast addresses they are interested in to the border router, and the border router maintains a multicast listener table and performs the multicast forwarding. So any multicast messages come to the thread network that will use the MPL protocol. Yeah, as we already discussed, the thread provides the IPv6 interface to the app layers. However, there are some limitations on the availability of IPv6 connectivity in the public IP networks. To enable thread devices to connect to public IP networks and facilitate the end-to-end communication between thread devices and cloud services, the border router needs to implement the DNS64 and NAT64. This mechanism performs mapping and translation between the IPv4 and the IPv6 addresses, allowing the seamless integration of Thread devices with IPv4-based networks. So here we also give an example. If we want to know the address of the expressive website, we do a query, and we will get the mapped IPv6 address. And then we use this address to do the communication. Okay, then we come to the second part. We will talk about how Thread works in a Meta ecosystem. So you know Thread is a network protocol. There are several applications that can work over Thread, like the HomeKit, Weave, and Matter. Matter is currently becoming more and more popular. So here we take Matter as an example. Matter is an application protocol that runs over IP networks. Currently, it supports Ethernet, Wi-Fi, and Thread. These three networking protocols also provide the IP interface. In a typical Matter topology on the right, there are Matter over Wi-Fi and Matter over Ethernet devices, and a phone as the Matter commissioner and controller, and also the Matter over Thread devices, as well as the Thread border router. So it's a very typical Matter topology in the real life. The Thread border router helps to forward IP messages between Thread and non-Thread networks. So all these Matter devices can communicate with each other end-to-end within the local network without the need to go through a cloud or any kind of gateway device. From the Wi-Fi to the Thread, from the phone to the Thread, or between two Thread devices from different positions, these all can communicate to each other end-to-end. And in Matter, it uses the DNS-based service discovery, which is supported by Thread border router as well. The Matter devices, whether they are from Wi-Fi or Thread, can discover each other. The only difference is that the multicast DNS is used in Wi-Fi or Ethernet, while the unicast is used in Thread. For example, when the phone app controller wants to find a Matter over Thread device, it will send a multicast query in Wi-Fi network. Since the BR knows the service, which was already registered by one of the Thread devices, then the BR will respond the query to let the controller know the Thread device's address. And of course, when the controller wants to send a message to the Thread device, it knows the route, as we introduced just now. So it will send the message to the border router first, and the border router will perform the IP layer message forwarding to the Thread device. Matter also has a group feature, which is based on multicast. Once a Thread device joins a Matter group, it will register the corresponding multicast address to the border router. The border router will help to listen and forward the multicast message. Of course, the suitable MPL protocol is used in a Thread network for multicast. Now, the last part is about the Thread solutions we can provide. Espressif offers hardware platform solutions for Thread. Now we have two SoCs that support Thread, which is 15.4, the ESP32H2 and ESP32C6. Both SoCs are production ready. The ESP32H2 is a BLE and a 15.4 combo SoC, while the ESP32C6 is a 3-in-1 SoC supporting Wi-Fi 6, BLE, and 15.4. So our customers can choose either the H2 or C6 to build Matter devices, Matter over Thread devices. Moreover, by combining Espressif Wi-Fi and the 15.4 SoC, We can also offer Thread Border Router and ZigBee Gateway solutions. In these setups, one Wi-Fi SoC serves as the host, with an H2 used to extend the 15.4 interface. However, some developers may ask about using a single C6 to build a Thread Border Router, but actually it's not recommended, as the C6 has only one IF path, which means the Wi-Fi and Thread can't receive at the same time, leading to high packet loss rates. As a result, we recommend the two SoC solution for ESP Thread Border Router, which ensures the good performance and the efficiency. The Espresso Thread SDK is built on top of ESP IDF and OpenThread, and both ESP32C6 and ESP32H2 are officially supported since IDF 5.1 version, as well as the Thread SDK and the Border Router SDK. And I also want to note that the C6H2 and the ESP Thread Border Router solution are all Thread 1.3 certified components. And below are some useful links. The Thread SDK and the Thread examples are all in the ESP IDF itself. And we provide some additional Border Router production features and examples in the ESP Thread BR repo. If you want to build a Matter over Thread product, the ESP Matter is the correct SDK. Now let's look into the ESP Thread Border Router solution. It's an RTOS-based Thread Border Router solution, which is different from the commonly used OTBR POSIX solution, which is Linux-based. This means that the ESP Border Router solution is very cost-effective. It fully supports all the Thread Border Router features, including the bidirectional IPv6 connectivity to both Wi-Fi or Ethernet, as well as the service discovery, multicast, and NAT64. In addition, it also provides some more production features, such as the RC update, since the solution involves two SoCs and requires the download of two matching formulas for OTA. So the SDK offers a mechanism that combines the two formulas into a single binary. With a one-step OTA process, the host SoC will automatically download the RCP formula to the 15.4 SoC during the initial boot. And the IF coexistence design is often a challenging aspect for devices which have multiple radios. So in our Border Router SDK, we have the integrated hardware and software design, which offers the 3-wise PTA coexistence feature. So this feature helps a lot to simplify the complexity in the customer's application. And additionally, the SDK offers a user-friendly web GUI for easier configuration by the user. Moreover, the provided REST API are compliant with the APIs offered by the OTBR POSIX to ensure the compliability and seamless integration. And finally, the Thread device can also integrate with Espressif's Rainmake cloud solution, which allows the Thread devices to be connected to the Rainmake cloud service via any NAT64-enabled Border Router. This means that any cloud-based solutions, such as the remote control, OTA, and device management, all can be supported on the Thread products. The only requirement is the Border Router has to support the NAT64 feature. Yeah, the end. So thanks for watching, and feel free to reach out to us for any further inquiries. Thank you.